This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, the professor for this class, and this is lecture 45 on lithography, illuminating the mask. In the last two lectures, we talked about, well, I guess it's the last three lectures, we talked about diffraction and then forming an image. Now that I think about it, 4 lectures. The last 4 lectures, we talked about diffraction and forming an image, but we assumed a particular type of illumination. We assumed that the illumination would be normally incident on the mask. It was a very reasonable assumption. Simplifying assumption made all the calculations a little bit easier. But now let's generalize. Instead of light just hitting the mask normally incident, what if we simply tilt the plane wave of illumination? Now the light's coming in from an angle. Should be fairly easy to do. What is its impact on the diffraction pattern, and what's the impact on the image? We're going to find out. So we tilt the illumination. I'll let theta prime be the angle that the light hits the mask. Now I'll still call the zero order the light that goes through without changing its direction, and then we'll have a plus first order and a minus first order on either side of that. We'll use our simple mask pattern of equal lines and spaces with a pitch of P because that's the easiest mask pattern to use. We've already looked at it in some detail, so we know what to expect. So what is the impact? We can look carefully at the Fourier transform relationship, and we see by applying the shift theorem that it's a very simple answer. We get the exact same diffraction pattern. However, it has been shifted by a spatial frequency equal to sine of this theta prime, the angle that the light hit the mask, divided by the wavelength lambda, which makes perfect sense. I've simply taken the same diffraction pattern I had before and shifted it. The zero order lands right where you'd expect it to land, with the light coming in at an angle. It hits the lens, shifted over to the side. So, sounds like everything's pretty simple. Not much different, except when we think about the lens. Now the lens is fixed in place. After all, it's a very big object. In lithographic systems, lenses are hundreds or thousands of pounds. They're very, very large. They're not going anywhere. They're not moving. That lens is stationary. So if I shift the diffraction pattern with respect to the center of the lens, right? So the center of the lens is this little dash, and it's where the zero order was when I had normally incident light. Now it's all been shifted. The lens has a certain opening, a radius, NA over lambda, here and here. And if I shift the diffraction pattern, what happens? I can change which diffracted orders go through the lens. Now before, when I had normally incident light in this particular pitch, in this particular NA and wavelength, what I saw was a diffraction pattern with 3 diffracted orders making it into the lens. Now I've shifted it, and only 2 of those diffracted orders make it through the lens. What do you think is going to happen? Well, we saw last time that the more diffracted orders you capture, the better the quality of the image. So in this particular case, shifting by this amount results in an image that will be inferior to the normally incident image. It's only capturing 2 orders instead of 3. But wait. That's specific to this situation. What if, for example, I had a larger NA on my lens? Remember, NA is the sign of the maximum half angle of light that can be captured by that lens, multiplied by the refractive index of the media. So here I have a higher NA, so my cutoff frequency is larger. And guess what? I still capture these 3 diffracted orders through this lens, plus, oh look at this, I've captured this 4th diffracted order, which is a -3 order. So that makes it through the lens as well. Well, does that make the image better? In the circumstances we've talked about so far, the answer is yes. So what does tilting the illumination do? Does it make it better? Does it make it worse? Well, I think the correct answer is yes. Sometimes it makes it better, sometimes it makes it worse. It very much depends on the specifics, in particular the specific mask pattern. Do I have this pitch or that pitch? And a particular NA and lambda as well. So one of the things we'll learn all through this section on illuminating the mask is that the impact of tilting the illumination is not always going to be obvious, and it will depend on the mask pattern we're using. All right, well, with that said, let's talk about something that seems like it might be a different subject, but it's really not. Resolution. What is the smallest pattern that I can print? Resolution is basically defined something like that. The smallest feature I can print of a certain type. Sometimes we might say the smallest feature I can print with acceptable process control or acceptable manufacturing yield or something like that. But we'll make it very simple in this case. I'll call it the theoretical resolution, and it will simply be the smallest pattern I can print, where printing means I get any kind of an image that resembles the mask. Even if it's a low quality image, it doesn't matter. If I get any image that looks like the mask, I'll say it is resolved. Right? So very simple definition. Now, I will then look at a specific feature, equal lines and spaces, or just lines and spaces in general of a pitch P. And I'll ask, what's the smallest pitch that enables me to still get an image? Well, that's a very narrow definition of resolution, and you can have much broader definitions than this, but this will serve our purposes. What is the smallest pitch of a line space pattern that I can print, where printing means I get any image whatsoever? Well, let's think about it for a second. Suppose I have normally incident illumination on my mask. I get 0, plus and minus first orders. How many orders do I have to capture to get an image? Well, I'll give you a very simple answer. At least 2. 2 orders gives us 2 plane waves hitting the wafer. 2 plane waves hitting the wafer coming from different angles will result in an interference pattern, and it's that interference pattern which we call the image, and that's what we'll print. If I only get 1 diffracted order going through the lens, I get 1 plane wave, well, that's nothing more than uniform light. If only 1 diffracted order goes through the lens, I get a uniform blanket exposure of light on the wafer, and there is no image. So, if I'm going to capture at least 2 orders, what is the smallest pitch? Well, I start making the pitch smaller and smaller, and what happens? This angle of diffraction gets bigger, right? And the first order moves further and further away from the center of the lens. What's the smallest pitch I can print? That pitch which puts the first order right at the edge of the objective lens. In other words, the position in spatial frequency terms of that first order is 1 over the pitch. And if I put that first order right at the edge of the lens, it's right at the cutoff frequency for that lens, which is NA over lambda. So the smallest pitch I can print, P min, 1 over P min must equal NA over lambda. So let me rearrange that and define something called the minimum half pitch. I'll use the term R for resolution. And this is what I'll mean by resolution, the smallest half pitch that I can print. So R will be P min over 2, and it's simply 0.5 lambda over NA. That's our theoretical resolution for normally incident light. Now, let's see how this situation changes when we tilt the illumination. So I'm going to tilt the illumination, but not just any old tilt. I'm going to pick a very specific tilt. Here's what I'll do. I'll tilt the illumination so that the 0 order of light, which goes straight through without changing direction, just makes it through this edge of the lens. So the 0 order is over here. Obviously, the plus first order will never go through the lens. But I can still capture the minus first order. And if I get 2 diffracted orders going through the lens, I'll get 2 plane waves interfering at the wafer, and I'll get an image. Well, it may not be as good a quality of image as when I had 3 diffracted orders, but nonetheless, it will be an image, and I'll say it is resolved. So now the zero order is always fixed in this position. I decrease the pitch, and the minus first order moves further and further and further away until at the smallest pitch possible, the minus first order just barely makes it through the left edge of the objective lens. When does that happen? Well, this diffraction angle, when it's at its maximum, is not the radius of the lens anymore, it's the diameter of the lens. And so the sine of theta max is going to be 2 times NA. And that will be lambda over P min for that constructive interference diffracted order, for the first order. As a result, the minimum half pitch R is not 0.5 lambda over NA anymore, it is 0.25 lambda over NA. In other words, by tilting the illumination so that the zero order just makes it through one edge of the lens, I am able to print patterns with half of the pitch that I could print before. We have a name for these two situations. On the left we call it 3-beam imaging, and on the right we call it 2-beam imaging. I bet you can't guess why we came up with those names. If I have 3 diffracted orders through the lens, I call it 3-beam imaging. If I have 2 diffracted orders through the lens, I call it 2-beam imaging. With 2-beam imaging, I can get twice the resolution as I could with 3-beam imaging. Twice as good a resolution. That is, R is cut in half. Well, the name of the game in lithography is resolution. Well, at least it's one of the names of the game. There's other important things too, but we are always striving for better resolution. So you can imagine our goal is going to be getting 2-beam imaging so that we can push our resolving power down closer to 0.25 lambda over NA. Now, let me generalize what we've just learned. We said the resolution, which I'll call the minimum half pitch that I can print, is some constant K1 times lambda over NA. When I had 3-beam imaging, K1 is on the order of 0.5 or bigger. Right? Sometimes we can't push it all the way to the theoretical limit, but we can get close, so that limit is 0.5. For 2-beam imaging, K1 has to be bigger than 0.25. And again, we often can't push it right to its very limits, but we can get it close to about 0.25. And that's the cutoff for 2-beam imaging. All well and good. How do we actually do this in practice? I've talked about a plane wave illumination striking the photomask normally incident, and I've talked about plane wave illumination striking the mask at an angle. Let's see how we might generate those types of illumination. I'm going to consider a point source. Remember, a point source of light is light that emits waves that are spherical in shape. Spherical waves coming out of that point source. So here's my point source, and I have these spherical waves propagating away from the source. Now I'm going to put a lens, the condenser lens, as a matter of fact, which we've seen before. It will sit such that this point is exactly at the focal point of this lens. Now, if you haven't studied optics or know much about lenses, you may not realize this, but a point source generating spherical waves, when placed at the focal point of the lens, will produce plane waves coming out the other side of that lens. That's just the way it works. You think of it in reverse. If all the light were parallel and coming in to the lens in this direction, it would all focus down to the focal point. That's kind of the definition of the focal point. And lenses are symmetric. You can just reverse the direction of the rays and everything works the same. So light emanating from the focal point will turn into light coming parallel with the optical axis out of that lens. What do I have illuminating the mask? Normally plane wave illumination, just like what we've talked about at first. Now we'll do something simple. Let me simply take that point source and put it off of the optical axis. Remember, the optical axis is a line going through the dead center of the optical system. If I put this point in the same position but off axis, same distance away from the lens, I will still get plane waves coming out of that lens, but now those plane waves will be tilted. They'll come out at an angle. How big of an angle? Depends on how far off from the center line I make this point source. So the farther off the point source, the bigger the angle. And I get oblique illumination of the photomask, just like we saw in our second case. So what do we do in reality? Do we use on-axis points or off-axis points? The answer is yes. We use both. We use an extended source. We don't use point sources of light to illuminate our masks. We use big spots of light for a couple of reasons. One is we want lots of energy, and a big spot of light gives us more energy. But also, we want to use the effects that we're about to describe. An extended source of light, a big spot, can be thought of as a collection of individual points. Now, we just saw what an individual point will do. Every point in that source will produce one plane wave of illumination striking the mask. So a point right in the center of the optical axis will produce plane waves normally incident on the mask. But a point down off axis will produce a plane wave coming up and hitting the mask. A point towards the top of the source will produce a different plane wave coming down and hitting the mask. In other words, when I extend the size of the source, it's equivalent to saying I have a range of angles striking the mask. Every point on the source produces a different direction of light hitting the mask. When this happens, we call it partial coherence. So let me explain what I mean by this. First of all, the term coherence can be confusing for one specific reason. There are two kinds of coherences that we talk about: spatial coherence and temporal coherence. They are related to each other, but they're different. Temporal coherence has to do with the behavior of light over time, how well it keeps its phase relationship at two different points in time. Spatial coherence has to do with the phase relationship in space. And because we're talking about extending our source through space, we use the term spatial coherence for the illumination. Often in lithography, we drop the word spatial and we only say the coherence of the illumination. And that can be confusing because some people might think we're talking about the temporal coherence, especially if we use laser light sources. But that's not what we're talking about. When we say coherence of illumination of the mask, we're talking about the spatial coherence. So we can define a term called spatially coherent illumination, or as I said, we often just say coherent illumination. What does that mean? It means very simply light hits the mask from one direction only. If light hits the mask from one direction only, we say we have illuminated that mask with spatially coherent illumination. Now, by convention, if we don't say anything else, when we say coherent illumination, we always mean that the one direction is normally incident. But that's not really a definition, that's more of a convention. You should specify which direction you're talking about if it's coherent illumination. But generally, if we say coherent illumination, we mean normally incident light. How do we generate coherent illumination? From a point source. So whenever we have a point source of illumination, we can generate coherent illumination that hits the mask from one direction. Now, what's the opposite of coherent illumination? Incoherent illumination. What is incoherent illumination? It means the light hits the mask from all possible directions. That is, instead of just normally incident, I get light from plus and minus 90 degrees hitting the mask. Of course, not just left to right, but also front to back. A cone of all possible angles. We call that incoherent illumination. And if you look up from the mask and say, how big is the mask that's illuminating it? Well, if light's coming from all possible directions, we can think of that light source as being infinitely big. So the opposite of an infinitely small point source of illumination is an infinitely big light source, and that produces incoherent illumination. Now, incoherent illumination is very important for some tasks in optics, in particular photography. Why? Well, most of our photographs are taken in available light. room lighting, outdoor lighting. And that light is bouncing off of all the objects and everything in space all around us. The thing that you're taking a photograph of is being incoherently illuminated. Light's coming at it from all possible directions. So when we talk about imaging in the sense of photography, the illumination that's interesting is usually incoherent illumination. But in lithography, we get to pick our own illumination. We can pick however we want to illuminate that mask. And the way we choose to do it is something in between these two extremes, something we call partially coherent. In particular, partially spatially coherent illumination. What does that mean? It means we have a finite but non-zero range of incident angles striking the mask. In other words, the angle range is more than just one angle, but it's not all possible angles. It doesn't go all the way out to plus or minus 90 degrees. This is equivalent to saying we have a source of light that's bigger than a point, but it's not infinitely big. It's a finite-sized light source. That's partially coherent. This is the type of illumination that we use in our lithography tools. Let's consider what happens when we use partially coherent illumination in lithography. We'll use as our example, the same example we've been using all along, a pattern of equal lines and spaces of certain pitch P with now normally incident illumination, so that we get our diffraction pattern seen here, zero order in the middle, plus or minus first order on either side. Now that's with normally incident illumination. If I were to come and tilt the illumination at an angle, what's going to happen? Well, it's going to shift the diffraction pattern off to the side by the amount that I've tilted. What if I were to tilt it the other direction? So like this instead. Well, it would shift the other way. And if I use a range of tilts, a range of angles striking the mask, I'm going to have a range of shifts of that diffraction pattern. So instead of the diffraction pattern being an individual point of light, I'll shift it back and forth over a range of angles that will turn that point into a spot of light. So here's the case where I have set sigma equal to 0.25. I'll explain what sigma means in a moment. But it's a certain level of partial coherence where I have a certain range of angles striking the mask. The result is the spreading out, smearing out of the diffraction orders from being, instead of individual points of light, large spots of light. Well, this is a cross-sectional view or a side view of the diffraction pattern. Let's look at it top down. Here I show a bigger spot, and the spot for the zero order, the first order, or the minus first order, each represents the size of the light source. The size of the light source determines the range of angles striking the mask. The range of angles striking the mask determines the shifting of the diffracted order into a larger spot. That larger spot is the same size as the original source of light. So my zero order is a spot that reproduces the shape and size of the light source. My first order is exactly centered where we thought the first order would be, at a spatial frequency of 1 over the pitch. But now, instead of being a point, it spreads out into a spot. Again, the size of that spot is the same shape and size as the light source we're using. Same thing, the minus first order, it's centered at a position of minus 1 over the pitch, but its size and shape is determined by the light source size and shape. How does this impact imaging? Well, I think you can see that all of the zero order is captured, but not all of the first orders. See, the plus first order, some of this is captured, because here I show the outline of the objective lens, but there's a region over here which is left out. This region is lost. It's part of the plus first order which is not captured. Over here I have part of the minus first order that's not captured. So some of the zero order has two other beams to interfere with. In other words, part of this zeroth order and first order and minus first order and plus first order is 3-beam imaging. But there's a region where some of the plus first is lost, and over here some of the minus first. Those are regions where I'll have only 2-beam imaging. So with partial coherence, what we usually get is some combination of 2-beam and 3-beam imaging. So the way we think about partial coherence is like this. Suppose we have a circular shaped source. We can describe this shape in two equivalent ways. The only thing we really need to know is the size. If I tell you it's circular in shape, I can tell you everything if I tell you the size of that source. So I'll explain the size of the source in the following way. I will tell you the size of the spot at the objective lens entrance pupil, or I'll tell you the range of angles striking the mask. Either one, I've told you everything there is to know about the size of that circular source. Then I'll define something I'll call the partial coherence factor. The partial coherence factor is defined as the diameter of the illumination spot divided by the diameter of the objective lens entrance pupil, or the sine of the range of angles hitting the mask divided by the acceptance range of angles of the objective lens, or NA naught for the numerical aperture of the objective lens. So if I go back to this picture, I can define the partial coherence factor, which I'll give it the letter sigma, as being the diameter of the zero order spot divided by the diameter of the lens. Now remember, lenses are sometimes called, entrances to lenses are sometimes called pupils. Aperture and pupil mean the same thing. So another name for the partial coherence factor is the pupil filling function. I've got a pupil. How much of that pupil do I fill with zero order light? Here I show a case of 0.5. The diameter of this is 0.5 of the diameter of the lens itself. I filled 50% of that diameter with illumination light, zeroth order light. So we say sigma of 0.5. Now equivalently, I could find the range of angles hitting the mask, and then take the sine of the maximum half angle of light hitting the mask divided by the sine of the maximum half angle of light that the objective lens could possibly capture, and that ratio is also the exact same value of sigma, the partial coherence factor. And in order to explain to somebody how you're illuminating the mask, this is the parameter you would tell them. You'd say, oh, I'm using a partial coherence factor of 0.5 or 0.3 or 0.7, something like that. What are the possible ranges? Well, it's possible to have sigma of 0. If I have sigma of 0, the diameter of my point goes to 0, and I've got a point source illumination. So this is what we've called already coherent illumination. Sigma equal to 0 is the same as coherent illumination. At the other extreme, if I let sigma go to infinity, I didn't quite draw it as infinity here, right? But I drew it very big to represent that it's much bigger than the objective lens itself. We can let sigma go to infinity. That means incoherent illumination. So on the other extreme, incoherent illumination, we describe sigma equal to infinity, and sigma values between these two extremes are called partially coherent illumination. Now in practice, there's no reason we would ever want sigma bigger than 1, because all of that light that doesn't go through the lens is wasted light. So in reality, sigma values for partially coherent illumination are in the range of 0 to 1. And typical values are more like 0.3 to 0.8. But we don't have to have circular shaped light source. What we call a conventional light source or circular or disc shaped light source isn't the only shape that we could possibly have. We could have other shapes. For example, an annular light source. An annular light source has darkness in the middle and then an annular disk of light, or a donut shape of light. And I would describe it by an inner sigma and an outer sigma. So where it starts and where it ends relative to the diameter of the lens. So an inner sigma and an outer sigma. But There are other shapes possible too. On the right, I show quadrupole illumination, where I have 4 spots of light. Another popular one is dipole illumination, where I have just 2 spots of light, one on the right, one on the left. The idea behind these odd shapes, things that are other than just a circle or a disk of light, is to try to achieve two-beam imaging for certain mass patterns. And we do that by essentially tilting the light. I mean, when I illuminate only with light off axis, I'm creating tilted illumination. And the tilted illumination is what gets me two-beam imaging. And by not having any illumination in the middle, I eliminate the possibility of three-beam imaging. So we use what is called off-axis illumination, or OAI. We love three-letter acronyms in the world of semiconductor processing. Off-axis illumination is, the purpose is to enable two-beam imaging. But that depends on the mask pattern. We have to get the right illumination shape for the right mask pattern. And in fact, sometimes we'll make custom shapes of illumination for very specific shapes of mask patterns that we're trying to print. There's a wide range of possible source shapes, and the design of these source shapes is a part of what lithographers do when they're designing a lithography process. So, how do we calculate a partially coherent image? We saw in the last lecture that we could calculate the image coming from equal lines and spaces and striking the wafer. We actually derived the exact equation for the case of three-beam imaging. Right? We could also derive a case for two-beam imaging. But we assumed coherent illumination, normally incident illumination on the mask. What if we have partially coherent illumination? Well, we use a property of the source that enables superposition. Each point in the source will produce its own image at the wafer. Different points will produce different images because different points will shift the diffraction pattern different amounts, and therefore I'll have different numbers of diffracted orders going through the lens. We adjust our source so that every point on the source is independent of all the other points. They don't talk to each other. They don't have any phase relationship with respect to each other. So every point we say is incoherently related to the other points. As a result, I can take every point in the source and calculate the intensity of the image that comes from that point and superimpose upon it all the other images from all the other points in the source. This idea of superposition of image intensities is the way in which we calculate a partially coherent image. Well, that's just difficult enough that we tend not to do it by hand. We don't do it with pencil and paper, probably not even with a spreadsheet. In fact, we just write software to do the calculations for us, and these software programs have become extremely popular to do these kinds of calculations. We call them lithography simulators, and they perform these calculations for us. All right, let's review what we've learned about illumination. Oblique mask illumination results in a shift in the position of the diffraction pattern. The amount of the shift, of course, is related to the angle of incidence of the oblique illumination. In spatial frequency terms, the shift is equal to the sine of the oblique angle divided by the wavelength. We define partial coherence as the sine of the maximum half angle of light illuminating the mask divided by the objective lens numerical aperture. For coherent illumination, we have one angle illuminating the mask, so sigma equals 0. For incoherent illumination, we have all angles illuminating the mask, so sigma equals infinity. And for partially coherent illumination, we have angles that are in between these two extremes. And finally, we learned about resolution, our first attempt to define the resolution of a lithographic process. We defined it only for the case of lines and spaces, and we talked about the minimum half pitch. We saw that For 3-beam imaging, we could get the best case for coherent illumination of 0.5 lambda over NA. But for properly tilted 2-beam imaging, we can double the resolution. That is, a resolution minimum half pitch of 0.5 lambda over NA. Excuse me. That's what 3-beam imaging is. Excuse me. 0.25 lambda over NA is the maximum possible resolution for properly tilted 2-beam illumination. So, what have we learned in lecture 45? You should be able to quickly and easily answer these questions. If not, you need to go back and review the material. How does oblique illumination affect the diffraction pattern? What is the Rayleigh resolution criterion? What are the minimum values of K1? Well, there's a hint. K1's in the Rayleigh equation for resolution. What are the minimum values of K1 for 2-beam and 3-beam imaging? Define coherent, incoherent, and partially coherent illumination. And recall that that means spatially coherent, spatially incoherent, and partially spatially coherent illumination. And finally, what is off-axis illumination? Still plenty of more to come in our lectures on lithography. Till next time.